Okay, welcome everyone to our 11th lecture. And today we're going to start looking into a very fascinating subject, and that's quantum computing. I will say that before the dramatic emergence of ChatGPT about 2.5 years ago, that was the deep tech talk of the day. In other words, every investor that was looking for deep technology investment at the time would look at quantum computing because it has a lot of promises. But then came ChatGPT, and to be honest, also personally, I've changed my focus. I was very busy investigating and doing research on quantum computing. But when ChatGPT came, I did shift to AI because it's wider and it has a much larger impact on humanity, not only larger, but also very immediate. Having said that, quantum computing is an amazing area, and we will also discuss the possibility of this technology interfacing with machine learning. Now, I know that some of the listeners are biologists, and I assume that maybe you're not familiar with complex numbers. We will need the very basic knowledge of complex numbers. Basically just multiplying complex numbers and the adjoint of complex numbers. Very, very simple things. But I decided, since I did not prepare you for this, to go through this presentation almost without mentioning complex numbers. I had to do a lot of acrobatics for it. But for the next lecture, you will all have to go through the very basics of complex numbers. It's critical to understand quantum mechanics and quantum computing, but today we're going to survive the day without it. So basically, what's a quantum computer? It's a machine that's based on the principles of quantum mechanics. Instead of using bits, it uses something which is called a qubit. A qubit is an element that can have an infinite number of positions, but when it's measured, it becomes either a 0 or a 1. In other words, it becomes a classical bit. Quantum computers are not going to replace regular computers. They're just good for very different tasks, actually a very small set of tasks. But the problem that the quantum computer solves, it can sometimes solve it exponentially faster than a regular computer. So a computation that may take 1 billion years can be solved in a few minutes with a quantum computer. The area that is of most interest in quantum computing is security and encryption, because apparently there are some algorithms that may be able to break the common encryption methods used today. And obviously that has a unique impact on the economy. Imagine someone having the passwords for Amazon shopping. I don't even have to start to explain what it would mean to the world economy. But this is an area where quantum computing is going to be at its main glory. And I can tell you that there are rumors that some countries are already downloading huge amounts of unencrypted data with the assumption that perhaps in a few years they'll be able to encrypt it and discover many secrets. I can also tell you that areas like Bitcoin and blockchain, people that deal with this technology also have concerns about quantum computing one day jeopardizing or compromising security. There are some directions and initiatives to combine quantum computing and machine learning. There's TensorFlow Quantum, QML. I hope we'll get to talk to it during our last lecture. And most importantly, the reason that quantum computing is basically stumbling for many years is because there are engineering challenges. It's very, very difficult from an engineering perspective to build a quantum computer. And that's basically stopping the whole flood. But once companies will be able to create computers with 50, 60 qubits, 100 qubits, which are stable, the world may change in many ways. Okay, so today we're going to talk a little bit about waves, about interference. We're going to talk about the famous double slit experiment. We will talk about the Copenhagen interpretations, the big debate between Einstein and Bohr. We'll talk about EPR, and then we'll gradually start working on real quantum circuits. Towards the end of the lesson today, we will build a real quantum circuit, which in all generality can be run on a real quantum computer of IBM. IBM is a cloud quantum computer, and we can actually run a quantum algorithm on their computer, on the real quantum computer. So we may end the day by writing together some code that will run on a quantum computer. So before we start, just the basics of the basics of the basics, I want to remind us what is adding, how to add functions. And this, what you're seeing now is one prompt in Claude, I think. And what I want to show you is how I'm adding two functions. So this is a sine, this is a cosine, and I can change, let's say, the amplitude of the cosine, or I can put it here, and I can just show the sum, and that's the sum. The red is the sum of the two functions. I'm leaving you the link for this. You can play with it. You can even do the following. Let's do a clear all. Let's do a sine again. And I would like to just add my own function. Okay. And I can do show sum. And what you see in red is the sum of the blue things that I did with a cosine. So basically, adding function is very simple. You simply add the value of the function at the same x. So if this is -4, you add this number here and this number here, and you get the sum. Very simple. We can continue. The next thing I want to show is what happens when you want to add functions that are moving in time. And the best example we'll be using today is going to be just simple sine waves. Let's do a 2D visualization. And what you see here, maybe I'll stop it. We can discuss it a little bit. You're seeing two sources of sine waves. With your permission, let me just change the frequency a little bit. And actually, we can start with perhaps only one wave, and I'll take the amplitude of one of them to 0. So what we have here is one wave, as expected. I can actually do something nice and ask my simulation to show the areas of zeros in red. And as we are expecting, since it's a sine wave, the zero is propagating. The zeros are propagating because we have a sine wave and we have many zeros, etc. But let's now add this one back and see something interesting. So now when we look at both sources and ask to color the red area, the zero area in red, we see something which is really interesting. We see areas that stay red all the time. If you look at the mouse now, where my mouse is, it's red all the time. These reds are, of course, moving, but there are areas that are red all the time, which means that they are zero all the time. So think about it. When we had one source, we didn't have that situation. Maybe, well, I can do something like this. So I'm putting now a microphone, sorry. So I'm putting a microphone in one of these areas. See, it's right on the zero, the microphone. But when we had only one, okay, let's look at the result of what the microphone is seeing. So when we had one source, the microphone obviously was seeing a sine wave. But see what happens when we now add another source. It's pretty strange. The microphone is suddenly quiet. So we added another source, but we caused this area to be quiet. And just think about it. If these sources are sine waves, let's imagine a flute. A flute, Khalil, is something which is very close to a sine wave. So if these two were flutes, two people just playing the same note on a flute, and you would stand in an area like this, you would hear nothing in the general case. Or in an area like this, you would hear nothing. So wherever the reds are not moving, it means that these areas are quiet because the superposition of the two sine waves is completely destructive. Any questions? So let's see what we learned. We learned that if we take two sine waves and we superpose them on one on the other, and they have the same frequency and the same wavelength and the same amplitude, there will be areas that will be dark because of the destructive interference. So let's go and discuss now one of the most important experiments in the history of humanity. It's called the double slit experiment. Actually, we can do it in the kitchen with some very simple devices, but I would say it's one of the experiments that really changed science forever. So let's see what we do. We have a flashlight here, which is throwing photons at two slits. Let's just have photons. Sorry. Okay. So you see now the flashlight is shooting photons on the screen, and let's increase the firing rate. And you'll see something which is pretty interesting. So the photons are moving through the slits. There are only two slits here. We'll have to wait a few more seconds, and we'll see a pattern that is very weird. Give it a few more seconds. I'll give you a hint. You can see that there is more activity in the areas that you see in the graph, which, if you think about it, should remind us what we saw in the two sine waves. There were areas that were dark, that had no activity, and there were areas that were full. So you can see that the photons that we are shooting now are actually falling on the screen in a pattern which is very similar to superposition of two waves. So, up to here, so what? It means that light is a wave, right? And probably what happens when the light wave hits this screen, it breaks into two little sources. It's called the Huygens principle. We know it from physics. And what we're really seeing here is something which is very similar to that. Let me just so we shouldn't be really surprised. We're seeing something like this, right? See, we have here two sources, sorry. And we shouldn't be really, really surprised, right? Because light is a wave and we see an interference of a wave. But now it will start to become weird because it turns out that when you shoot the photons one by one, as you can see here, the same thing happens. In other words, if you shoot the photons one in an hour, imagine that every hour you have a photon. You will still have the same behavior that we see here. So that would probably force us to think that every photon goes through both of the slits at the same time, right? Because if a photon goes to one or the other slit, we should expect just to see two peaks. But if even when we shoot the photons once in every hour, we get an interference pattern, it means that every photon is a little wave. Every photon splits into two different little sources which interfere with one another. So that's obviously already an amazing revelation, because it means that when we say that light is waves, okay, makes sense. But every photon actually goes through both slits at the same time. And then came the real big shock when people said, okay, I have an idea. I have a measurement device here. And what I'll do now, I have a measurement device which will see if a photon is moving, if my photon, which I'm reminding you, is moving one every hour, I'm shooting a photon. So all I need to see is if this photon is going through this slit or that slit, and I can build a measurement apparatus. We'll talk about it in a minute. And this measurement apparatus will just tell me whether it's true that the photon went into the same slit, two slits at the same time, or decided to visit a certain one. And look what happens when we do the measurement on. When we start measuring the same system, we just turn on. You have to see this. You see, I'm turning on and off the measurement device. So when I turn on the measurement device, something miraculous happens. The photons start to behave as though they are classical particles. The trick where they're doing both slits at the same time, the minute they see someone look at them, they change their behavior. And you can see now that they're behaving like regular classical particles. You see, we have now, as expected, just two little heaps here. And this is the same behavior that we would see if we would just shoot, little balls through the slits. But just think how crazy it is. The minute I turn on the measurement device, the photon decide to behave in a different way. Now, think how crazy it is. Let's assume for a minute that the measurement device is here. Do you see where my mouse is, where the cursor is? It's very far from the slits. The minute I turn the measurement device, the photon, which just came from the photon gun, already know it, and they decide to behave as classical particles. It completely doesn't make sense. But as many times it happens with physics, that's the experiments. These are the results. Now we have to build a theory around it. And this is where one of the biggest dramas of the 20th century physics unfolded. Okay. Please let me know if we have any questions here until this slide.
What's the difference between measuring it ליד המסך בסוף, or the מסך עצמו is measuring it?
Are we talking about the measurement device?
Yeah.
Okay, so when the measurement device is acting, what happens is that the particles stop to play the quantum game. They are just behaving as though they're little balls, and they just hit the screen as always. But before you turned it on, the screen is actually acting as a measurement device. Okay, because as you saw on the screen, in areas where there's no wave function, there'll be no hits of the photons. Okay, so the minute we decided to turn on our measurement device, the whole experiment became a simple, boring, classical experiment. But when we turned it off, when we didn't look at the system, it started to behave crazy. Now, I have to see as we move along how deeply you want to go into it, but there are a lot of things I can tell you about the experiment that perhaps may make you less confused. But still, any way we look at it, something is crazy here. Why is it that when I turn a device, a photon, which just started in the back, talks to itself and says, listen, I have to play classical now. Someone is looking at me. I'm embarrassed. I have to change my behavior. But that's actually more or less what happens.
Yeah, but that happens also if the measurement device is beside the screen, after it passing the two holes.
Okay, if the measurement device interacts, and now we're getting to the heart of the problem. If the measurement device interacts with the photon will become classical. If the measurement device is not interacting and is measuring something else, everything will be as expected. But since you mentioned that point, let me just go through these three items, and I will go a little bit deeper to answer fully the question. It's an important question.
Okay.
So what have we learned so far? So that first of all, we see that there's a wave pattern interference, even if the photons are shot one by one, which means that every photon in itself behaves in a wavy way. It's not a combination of photons. Every photon has this behavior. And we look at the screen and we look at the pattern, we can also see that the photons have to visit both slits. Otherwise, we would not have interference. And then we saw the really, really crazy thing that the measurement caused the photon to randomly choose sides. The minute we turned on the measurement, or to be more correct, the minute the measurement device interacted with photons, they became regular particles and they had to randomly decide whether they're going to the right slit or the left slit. So first of all, the word randomly is critical here because this is really, really the first time that we see true randomness. Remember that in our second lecture, we talked about diffusion and throwing a dice, and I told you that none of this is really random. It's all our ignorance. When we throw a coin in the air to see if it's head or tails, actually it was all predetermined. We're just too slow to see it, but there was nothing random here. What we are seeing here is a historic and dramatic thing. The minute we turned on the device, we caused the photon to make a random decision. And that's the purest way of randomness that we have in the world. It's coming from the internals, from the heart of physics. Now, to answer your question about the measuring device, and here, I want to explain something that maybe will a little bit demystify the whole thing, but we're still looking at a huge, crazy revolution. Now, how do we measure a photon? Or how do we measure an electron? The way you measure an electron, for example, you shoot a photon on it, okay? So if you want to measure a photon, you have to do something to this photon. And if you're doing something to the photon, then okay, so why are you so surprised that your measurement changed reality? So when you look at an elephant, what happens is that photons from the elephant hit your retina. But the photon that hit the elephant and then hit your retina did not move, did not do anything to the elephant. So you could say that by looking at the elephant, by measuring the photons from the elephant, maybe something happened to the elephant. But if the elephant was very small, if for the size of an electron, then photons that hit it have to do something to the elephant. And obviously, we all know that quantum theory only deals with a very small and microscopic world. So to little bit demystify the measurement, the whole measurement thing, I would say that we have to understand that measurement means an interaction. And if you interact with something, don't be so surprised if you touched it or changed it. When you throw a photon at an elephant, you do nothing to it. But when you throw a photon on another photon or on an electron, then obviously it may be something different. So just already, again, to emphasize, we've met some crazy things in the last few minutes. One of the most important ones is that we have discovered at last randomness and unpredictability. Remember, in our first lectures, we talked about a deterministic world, but maybe not predictable. Here we have lost determinism in a way and lost predictability because, and give me a few more slides, I'll give more examples, but we can see that quantum systems do have inherent randomness in them and do have inherent unpredictability in them. And we all remember, we talked about free choice and free will, and I promised you that almost every area that we will discuss in our lectures will touch free will. So of course, now we are in the quantum area. This is the famous Schrodinger's cat. And we are seeing that quantum mechanics does have a positive impact in a way to those who think that we have free will, because at least now you cannot look at Laplace's demon and say everything is determined. To remind you, Laplace said, give me the momentum and position of every particle in the world, and I will tell you how everything will evolve. But according to quantum mechanics, as we will see, there's no such a thing as providing both position and velocity of a particle at the same time. You just can't do it inherently. So this and the predictability we discussed in a way saves us from the Laplace's demon scenario. Just to throw a little bit cold water on this camp, it's true that quantum mechanics does introduce new randomness and new unpredictability, but according to most views, and also my view, it doesn't solve the free will problem. We don't have time to discuss it. It's a deep discussion. Perhaps we'll leave some time in our last lecture and I'll explain more. But at least I want to emphasize that quantum mechanics introduces a big question into people that believe in determinism and no free will. It's not as simple as it was before we talked about quantum mechanics. Now we have true randomness, we have true unpredictability. Okay, so after this experiment and other similar experiment, a group of very smart people met for a few meetings actually, and in Copenhagen, and they all agreed on some kind of an interpretation for quantum mechanics. We will not go very deep into it, but we'll just see that they highlighted the main points that we just talked about. Superposition, a system can exist in a combination of possible states. I'm reminding you the photon was both on the right slit and the left slit until it was measured. And listen to this, collapse upon measurement. When the measurement takes place, the wave function, the quantum wave function suddenly collapses and the particle becomes a classical particle. Now that's an atomic bomb. First of all, physics don't really like the word collapse, singular. What does collapse mean? How fast does it happen? You have a function and suddenly it becomes a little needle. It sounds very, very unphysical and very strange. And a very smart physicist called Albert Einstein, as we'll see in a minute, did not really agree with the main principles of the Copenhagen interpretation. And a huge debate arose between Niels Bohr, who was more or less the founder and the leader of this interpretation, and Einstein. We will talk about it a lot in the coming few minutes, but just to explain that what happened, there were experiments and people had to create a story that will work, that will agree with the experiments. Now, the story is terrible. It's unintuitive. It makes no sense. But amazingly, quantum mechanics is the most accurate theory in the history of mankind in terms of its accuracy. So what humanity had to do now is accept a very crazy and illogical story, but a story which produces perfect results. Almost everything that we have now is a result of quantum mechanics. Computers, transistors, everything, all the technology, all the electronics, almost everything is related to these assumptions or similar assumptions. So what the folks in Copenhagen said, look, Mr. Einstein, we agree with you. We don't like it. But if we take this set of principles and a few more, by the way, I didn't mention here the Schrodinger's equations. We'll talk about it in 2 lessons from now. But if we agree on these crazy assumptions, we can create a theory that will predict everything. And as a physicist, that's your job. Your job as a physicist is to predict things. And this theory, if you agree to these crazy assumptions, you'll be able to predict things. Now, Einstein, just to remind you, it's after the special theory of relativity and the general theory of relativity, he was considered as God. And he said, look, this whole statistic thing, the probabilistic thing, and the fact that when you measure something happens, I don't buy it. And what I would like to do now is for a few minutes, try to build an intuition for you on what these principles of quantum mechanics are, and then later we'll see how Einstein tried to deal with them. Now, I wrote here, destroy after you watch, because some of the things I'm going to show you now are just my crazy inventions to help you create an intuition. They have nothing to do with real physics. Just to remind you, quantum mechanics deal with the microscopic world, and I'm going to show you examples from a macroscopic world where, of course, quantum mechanics does not live. So I'll start with the following story. Imagine that you have this father and his daughter went to Europe, and he wants to send her flowers for her birthday, but he doesn't know where she is. She could be in Paris, she could be in Rome, she could be in Madrid. He has no clue. So if we're looking at the pure quantum perspective, and if we were in a microscopic world, since he doesn't know where she is, then she's really in all 3 places. Listen to this. She is a superposition. She's in a superposition state, which means that she is in Rome, Paris, and Madrid. His sweet dear daughter is now in 3 places. Okay? But fortunately, he remembered that before she went abroad, they had an agreement that he can locate her by GPS. So he's working with the GPS, and look what happens. Sorry. Look what happens. She goes straight to Rome. Now, what happened here is something which is very similar to what we saw in the double slit experiment. You activated a measurement device, and the photon decided to behave classically, to make a choice whether it's going right or left, and behave classically. And that's exactly what happened to the daughter. The minute the father turned on the GPS and located her, in order to locate her, she's now in Paris. Now again, I know it's crazy, and of course it's irrelevant because we're talking about a very macroscopic world. But think about it, that when you're in the ignorance mode, when you don't have the information, the system can be in all possible places. And specifically here, it could be in 3 places. It could be in Paris, in Rome, or in Madrid, because the father knew that his daughter will only be in one of these 3 places. Now, he could say, look, she's probably in Madrid because she likes the weather more. So he could say the chances that she's in Madrid are higher. But the minute he does the measurement, his daughter, in a way, will have to make a decision whether she's in Madrid, Rome, or Paris. Now, the numbers that you see here are numbers that will show you what is the probability of her being in one of these places. You can see that if you square half, and 1 over square root of 2, you get 1. So you have here, the daughter has to be in one of these places, and we'll talk about in a minute why we square them. But the square of each one will tell you what is the probability to be here. And you can see that actually she had 50% chance to be in Madrid. Okay, because when you square this, you get 1/2. But when the measurement took place, she actually became an Italian. She's in Rome now. And you see now she has a chance of 1 being in Rome. Now there's no more quantum crap, sorry. Now it's classical. The minute we did the measurement, we're in a normal world now. Okay, so now she's back to regular. The daughter is in row now. Is this clear or not so clear? Again, I'm just trying to build an intuition. I want to show another thing that you will have to destroy after you watch, and that's an example I'd like to show. So you see, I have here, let me just show you. I have here, sorry, a little bottle. Here I have some pebbles, blue and red. And what I'm doing now is I'm taking a certain pebble and putting here. Now, you don't know what I have here, whether it's red or blue. I don't know either. Okay, now, according to Niels Bohr, or the Copenhagen interpretation, what I have here, what do you think? Do I have a red or a blue?
Half and half.
I have a superposition of red and blue. I have something strange here, which let's call it purple or half-half, whatever. But I don't have a red here and I don't have a blue here. The minute I look, it turns out that it's blue, okay? Now, we have to understand how different the Einstein view is from the Niels Bohr view. Einstein said, you idiot, it was blue all the time. You just didn't know that it was blue, but the fact that you did not know that it was blue or red doesn't mean that it wasn't red or blue. And Bohr says, no, before you measured, when you were in full ignorance mode, what you had here is a superposition of red and blue, whatever that means, purple, half-half, but you did not have here a blue or a red. By the way, one could ask, who cares? Who cares? I mean, would it make any difference? I mean, will the world be different if one of them is right? Turns out that absolutely is. Not only that, spoiler alert, Bohr was right. What we have here is not blue and it's not red, it's a superposition. Okay, and as you see, perhaps in this or the next lesson, it means a lot whether one of them was right. Now we have to understand Einstein obviously was one of the smartest people that walked on the face of the earth. What Einstein said, he didn't say that quantum mechanics is wrong. He looked at the amazing results of quantum mechanics and understood that there's something huge in this theory. He just said, it's not complete. We don't know everything about quantum mechanics. And you know something? This thing was really blue. And there may be hidden variables that I could measure and show everyone it's blue, but I just don't know what these hidden variables are. So Einstein claimed that there are other variables, that the theory is not complete. And what I had here before I measured was absolutely blue. I just couldn't see it. But if the theory was deeper, and if we could unravel these hidden variables, perhaps we would be able to show everyone that it was blue even before you watched it. Are we clear? Good. So just to show you some of the arguments that Einstein and Bohr had, they were, by the way, good friends. So Einstein said, do you really believe the moon is not there when you're not looking at it? Obviously, Bohr did not mean that because the moon is very macroscopic, but you know, it's Einstein. And then he said the famous word, God does not play dice with the universe. And Bohr said Einstein stopped telling God what to do. So that was the kind of discussions that they had between them. And again, the meaning when Einstein says God does not play dice with the universe, what he meant is that pure randomness that we talked about. Is the fact that when you measure something, when you measure a system, it suddenly does something very purely random. Okay? This is a very nice picture of the two. Even a nicer one. And okay, maybe we'll do just 1 minute of deeper philosophy before we move forwards. So, when you think about the measurement thing, obviously it's very strange. I'm looking at something, and the minute I'm looking at it, it behaves differently. Does this mean that my looking at the world or my consciousness affects the world? Very strange. Now, most physicists do not think so, but there are some very, very serious physicists like Roger Penrose, von Neumann, Wigner, and others that claim something which is just fantastic. Their claim is that our consciousness, the fact that we understand a result of a measurement or that we are a part of the measurement cycle has an effect on the world. Just, as I said, it's a minority. Most physicists do not think so. But just think what an amazing thought it is that if I did not look at the double slit experiments, it would be different experiment. The minute I look at it, the minute my conscience looks at the double slit experiment, the world changes. Now, obviously, you can ask some nice questions. What happens if a cat looks at the double slit at the measurement result? There's a whole bag of philosophy around this consciousness thing, and I would say that many so-called spiritual mentors take this to different areas, which are absolutely not correct from philosophical perspective. If you look at the argument between Deepak Chopra and Sam Harris, you'll see a very nice example of where these things are going.
May I please ask a question?
Yes, please. Yes, please.
You had this argument of Einstein that when you don't look at the moon, it isn't there, which is
Right.
obviously not true, but it does show kind of a very important point that the line between microscopic and macroscopic effects, in a statistical manner, is not a clear-cut line.
Of course it's not. Of course it's not. And we're going to talk about Schrodinger's cat and other things that really deal with this borderline. But as you mentioned, the moon thing was a half joke by Einstein. But you are right. I can tell you that some of the quantum effects that we are going to talk about, like teleportation, some claim that they can be also shown in a macroscopic world. So I agree. It's not a clear-cut line. I want to add a completely different kind of view, and that's the beauty of physics, where you can see how wide the spectrum of disagreements can be. So we talked about Roger Penrose and von Neumann, who, in a way, put the individual or the person in the center of the universe. Think about it. I'm looking at something, and my consciousness is doing something to the world. Again, that's the extreme view of it. And even Roger Penrose here said something which is not that direct. He said a scientific worldview which does not profoundly come in terms with the problem of conscious minds can have no serious pretensions of completeness. In other words, Roger Penrose feels that consciousness is a part of the game, is part of the physical game. As I said, there are others that take it even further and claim that consciousness itself is what's really controlling the world. Now, just to even things out, I want to show you what another British physicist, Stephen Hawking, said. And it's almost poetic, even though it's very depressing. The human race is just a chemical scum on a moderate-sized planet orbiting around a very average star, the sun. Okay, so we're just organic scum on a piece of rock, which is Earth, which is orbiting around a very unimportant star, which is the sun, in the outer suburbs of one of among 100 billion galaxies, another unimportant galaxy, the Milky Way. So you can see the amazing difference, almost poetic difference between Stephen Hawking, who we're just talking about our complete insignificance to Roger Penrose and other scientists who claim that we are actually the center of creation, that consciousness is really the center of creation. We will continue because it's not a philosophy class. And before we move forwards, I would like to take a little aside and talk about the speed of light. Unfortunately, in this course, we will not have time to have a lecture on relativity, so we missed that one. But I do want to take one important thing from that, and that is the speed of light. So we all know that the speed of light is constant and you cannot surpass the speed of light. That's one of Einstein's assumptions when he founded special relativity. I want to show you a little movie that exemplifies this idea. And let's look at it and then talk.
Yes.
So what you see here is you see Mount Vesuv in the year 79 when it erupted. And you will see that the picture of eruption is going to be obviously carried out everywhere because there are many photons there. So if I were here, I would see the eruption because photons from the mountain that hit the mountain hit my retina also. But most of the photons did not reach people's retinas. They just moved into space. So now we're going to look at a group of such photons.
79. Mount Vesuvius erupts.
Okay, you'll see on the right the photons that start moving towards space, carrying the picture
And
with.
from that fiery cloud, a group of photons escapes.
Okay, you can see here the picture of the eruption. And now it's an important opportunity for me to explain that the photons are carrying information with them. Okay, so the photons are carrying information about what happened when Vesuvius erupted. Let's continue. You can see, by the way, that now we are already in year 1697, and here we have already, early medieval kind of scenery. We're already in the year 900.
They've been flying ever since. And if there's a planet 2,000 light years,
Okay, we are getting closer to the Renaissance. You see the troubadours, and they're continuing their way into space.
those photons are arriving there.
Now, just for you to know, there are about 50,000 stars that are almost exactly 2,000 light years away from us, which means that there are about 50,000 stars that it would take a photon 2,000 years to reach from there to us or from us to them. It doesn't matter. And what happens after 2,000 years, these photons arrive at one of these stars, and they see a very curious alien. And I love his saying now.
Vesuvius erupt for the first time.
Man, did this mountain just explode?
Okay, man, did this mountain just explode? So what actually happened here is something weird. Now, as we speak now, someone out there is seeing the eruption of Vesuvius. And by the way, if it's 2,000 years ago, perhaps they can also see the destruction of Jerusalem 2,000 years ago. And by the way, if the star is 30 million light years away, they can see dinosaurs now, okay? It's important for me to emphasize. Now, theoretically speaking, of course, there are a bunch of people, not people actually, creatures that potentially...
Year 79.
That can potentially things that happened very, very far in our past. And when you think about it, when you look at the night sky, you're actually an archaeologist. You're seeing the past. When you see a star that is, let's say, 200 billion light years away, this star may not exist anymore. Maybe it died out. The photons that reach your retina started their journey 200 million light years ago, but when they reach the retina, the star may have already exploded. In the same way that our nice alien friend, He's seeing the eruption, but now there's probably a mall, a shopping mall in this area. So what I want to emphasize here is that
Year 79.
sorry, I want to talk now less about the speed of light, but the fact that the photons were carrying information with them. And I would try to correct the saying that the speed of light is cannot be surpassed. I would say it in a little bit different way. You cannot move information from one place to another faster than the speed of light. This is something that everyone would agree about. Any questions? Okay. So the argument continued to be heated. And in 1935, Einstein came to Europe to meet Bohr and all the other physicists with a huge bomb. It's called the EPR bomb. EPR is Einstein, Podolsky, and Rosen. Podolsky and Rosen were two, I think, PhD students, two of his PhD students. And together, these three came to Europe with the feeling that they've been able to drop the biggest bomb in quantum mechanics and prove that the whole Copenhagen approach was wrong. There must be hidden variables, and everyone was very happy. There was even a leak to the paper a day before they came, which I think caused Einstein not to speak with Rosen until the end of his life. I'm not sure whether it was Rosen or Podolsky, but he was very angry that there was a leakage about the bomb that they're going to throw. And I would like to show you what a brilliant idea they came with and how this idea became actually the big boomerang of Einstein and his school of thought. So what you see here is I have this glass with blue and red particles. And what I'm doing now is I'm taking one blue particle and putting in the white box here, and then another red particle and putting it, sorry, I'm actually not, I'm being blindfolded and just taking a particle without knowing which one is who, okay? So again, I have here two bottles. One of them is red and one of them is blue. I don't know which one of them is red and which one of them is blue, but for sure, one of them is red and one of them is blue, okay? So the question is, what happens if I open one of these boxes? So according to Einstein's view, you say, okay, Joshua, open this. It's blue. It means that the other one is red. It was blue all the time before. This one was red all along. Nothing really interesting happened. But, says Einstein to Bohr, let's look at this simple situation from your perspective. And again, I'm mixing in again. Now, according to Bohr, we have two purple, right? We have two superpositions. This one has a superposition and this one has a superposition. We don't know anything about the content of these boxes. The question is what happens now when I peek? So I peeked, and now the superposition of this bottle collapsed, the wave function collapsed, and I see a blue. Obviously, it means that the wave function collapsed also here. And I see red. So what's the big deal? And now comes the big bomb. Now Einstein said, let's do this experiment again. And here I'm adding my my angle. Imagine, just for the fun of it, that when the wave function collapses, it goes, okay, that there's a bombing noise. Something happens in the world, okay? So if we look at what happens here, according to Bohr, I looked at this here. There was one, when I looked at this box here, but immediately there was a here because the wave function collapsed by me looking at this one. In other words, the minute I collapsed the wave function of this white bottle, the wave function in the other one collapsed because we already know what it is. It's not in superposition anymore. If this one is red, this one is blue. If this one is blue, this one is red. Now, says Einstein, let's do the following. Let's do the experiment again, okay? Again, we have two bottles. We mix everything again. We don't know anything about the content of the balls. Now, I want to put this white box. I'm putting it on a very, very fast missile, which it can almost go in the speed of light. Let's say for 10 years. And during this journey, nobody's going to look at this, and nobody's going to look at these things, this either. They're called in physics world, they're entangled. There's some kind of a telepathy between them. Again, according to Einstein, there's no telepathy and no na'alayim. But according to Bohr, since we have two superposed wave function, and each one of them is dependent on the other, then what it means that there is some kind of a relationship between the two boxes, and now the missile landed 10 years later, and we have two bottles that are entangled. Nobody has looked at them yet. Nobody measured the bottles, but they're at a distance of 10 light years away. In other words, it will take a photon 10 years to move from here to here. Is this understood? Any questions?
Understood.
Perfect. Okay. Now says Einstein, dear Bohr, let's say I'm now looking at this, opening, doing the measurement. There's a big noise of collapse. But from your perspective, the other bottle will collapse immediately, instantly. Not in 10 years. And as you know, me, Einstein, I discovered that nothing can move faster than the speed of light. So please explain to me, dear Mr. Bohr, how is it that I was able to collapse? I was able to look at this box and immediately, instantly collapse the wave function in a place that is 10 light years away. In other words, there's no way for me to communicate, to send a photon faster than 10 years. Then how is it possible that I did an activity here which instantly created something to happen 10 light years away? Now, it is said that Bohr was shocked, went home depressed, and he thought that Einstein nailed it and was able to really not only collapse the wave function, but cause a collapse of the whole Copenhagen interpretation. Any questions? Do you understand, first of all, the brilliance of Einstein? So you probably want to know what is going on and what is the reality. So the amazing reality is that, yes, instantly and immediately, the collapse will happen in the far star, which is 10 light years away. But it is not really contradicting Einstein's theory, especially the little twist that I gave it. Remember that I said that it's not the speed of light, it's the speed of information. And what can be shown, and we will talk about it a lot in the next lecture, that when I looked at the first bottle, I did not send information to the other bottle. Yes, true, something happened to the other bottle immediately, but there's no way for me to send information faster than the speed of light. So if I want to send data or information, the speed of light is the limit. But the fact that there was a collapse of the wave function, which was instant, is not really a contradiction to the theory of relativity, because as we will show in the next lesson, there's no way to use this situation to move information from one another. Okay, we'll spend a few minutes in the next lecture, and I'll show you that if we were two people, very smart people, and trying to move information from one another, we would not be able to do it with the trick of collapsing the wave functions. So first of all, a sigh of relief. It's impossible to move information faster than the speed of light. And here Einstein was really badly boomeranged because about 30 years later, in 1965, an amazing Irish physicist called John Bell had an idea of creating an experiment which will prove whether or not there are hidden variables or not. And the amazing reality was that it was proved. There are many, many proofs and experiments, and again, it's the subject of our next lesson, that show that Bohr was right, that there are no hidden variables, and that before the measurement, the particles are always in superposition mode. Okay, so we'll have to wait until next lesson. I do want to move forwards, unless there are questions, principal and important questions about the flow of things until now.
Yeah, I have a question about the moving of information. If we determine before we send it that at the moment something occurs, we will send the data it occurred by collapsing the wave function. So,
But you did not send information. Sending information means that you send either a bit of 1 or 0 to the other side. This means that's the minimal possibility of information. If the other side, if we would find a way to move a bit, let's say a 1 bit or a 0 bit, and I know that it's a 1 or a 0, then I would move information. But here you already answered the question. Since I don't know before I measured whether it's a 1 or a 0, what I move to the other side is completely random. So I was not able to move information. Okay?
and if you take...
But please, let's leave this. It's the subject of the next lecture. Okay?
Okay.
But, obviously, I hope you at least understand my basic answer here, why I cannot move bits. Okay, speaking of bits and information, we're now getting into the crux of things, and we're going to start the first steps in understanding what is quantum computing. And by the way, very important, we are not going to talk in the next 2 lectures about quantum mechanics. Please bear in mind, I just talked about some principles of quantum mechanics, like superposition. But we didn't really talk about the big things. I mean, how do particles move in quantum mechanics? What does a magnetic field do? What does an electric field do? So the real physics is hiding in the Schrodinger equation, which we will get to in 3 lectures from now. But what I decided to do is to focus on quantum computing and to deliberately not teach you quantum mechanics now. Just the first principles. We can now go to quantum computing. You know all the physics you need to be a quantum computer scientist. But since I'm a physicist and I have loyalty to my profession, I will force you in the last lecture to really know what quantum mechanics is, and it's really, really beautiful. But since we're focusing on quantum computing, I just took a small piece from quantum mechanics, and that's the 2 interpretations from Copenhagen, the collapse of the wave function, the superposition. I'm just taking these 2 principles, and with these 2, it's basically enough to be a quantum computing scientist. As I said, we would need a little bit more complex algebra. We will also do without it now. We will bring it all to the next lecture. So let's talk about quantum computing and quantum bits. And I mentioned before that qubit is the most basic information element in quantum computing. We have a bit in a classical computer and a qubit in a quantum computer. And what is special about a qubit is that it's a quantum entity which can actually take an infinite number of positions. But when it's measured, it can be either a 1 or a 0. up or down. Okay, a little bit like the two photons that we showed, but the two photons, the superposition was just of two states. So the qubit is actually a complex entity with, as I said, an infinite number of states. But the beautiful thing is that when you measure it, it becomes classical. It becomes a 1 or a 0. And I think you can also already understand the genius behind quantum computing, and that is to do all the computation before the measurement. When you have the richness of superposition of elements that can be in almost an indefinite number of states and working and interacting with one another, and at the end you do the measurement, and it becomes boring and classical. But you let the party take place before the measurement when we are in the superposition state. That's the whole idea of quantum computing. Okay, so let's be a little bit mathematical. And again, I'm saving you complex numbers. It's very simple, but we will have to do it in the next lecture. So what we're going to do is agree that we have two states of a qubit. One of them we'll call it 1, 0. The other one is 0, 1. It's like a bit. Okay. Now, since a quantum entity can be a superposition, we can have here another qubit, this one psi, which is a superposition of 0 and 1. You see, it's square root of 3 over 2 times the 0, 1, and 1/2 times the 1. So first of all, you can already see that if we square this, we get a quarter. If we square this, we get 3/4, which means that before measurement, which means that this qubit is a superposition of the two basic bits, but it has a much higher chance, actually a threefold chance, to be in 0 mode because you have 3/4 here and 1/4 here. Okay, please stop me if you didn't understand this part. The rest will be very simple, but let's make sure that we understand this part. Okay, so we just defined one vector, a column vector, 1, 0, which we call 0, the other one 0, 1, which we call 1. And since these are quantum elements, by the way, they could be complex here, but these two are real. And since they're quantum elements, I can have another quantum qubit, which is a superposition of the two. So this qubit, psi, is a superposition of 0 and 1. It has a higher chance. If I do a measurement now, the system will go to either 1 or 0. You agree with me, right? It's like the Paris, Madrid, London. The minute you measure, boom, you have to land on one of them, on one of the options. So since one option is 1 and one option 0, a measurement will force me to be either a 0 or a 1. After the measurement, it's boring. We're going to be either here or here. The beautiful thing is that if I do this measurement 1,000 times on the same kind of qubit, about 750 will be 0 mode and 250 will be in 1 mode. Now this is really unimportant. Going to the next step, I could, instead of this 0, put here the original vector, multiply, add, and this means that this psi can be represented in this way as a column vector, which is square root of 3 over 2 and another half here, or in this way. In most cases, we will look at it this way. We will hardly look at the vector representation, but it's important for you to look at it now at least once. Are we okay? Again, we assume that we have a quantum element which is called 0, another quantum element which is called 1. They can be superposed to a third quantum element. This is a qubit also. So this qubit is really a superposition of these two basic qubits. If I do a measurement here on the psi here, I will either get a 1 or a 0. If I had, by the way, the same scalar here and here, I would have a 50% chance of giving 1 and 0, but I wanted to be a little bit more interesting, so I displayed it like this. Now the question is, okay, so you have a qubit, What do you do with it? What you do with it, you operate on it. So what I would like to show now is how we operate on qubits. And since qubits, as you can see here, okay, so this is the qubit 0, see, here, and this is the qubit 1, here. It's a column vector. If I want to change it, I have to multiply it by a matrix. So the first operator we're going to learn today is called the NOT gate. It's X. It's a 2/2 matrix. And look how nice it is. When I take this matrix and multiply it by this vector, we already know that it has to be a vector. Remember, a matrix times a vector is always a vector. But what you can see is that it became 1. In other words, when I did a NOT to 0, as expected, I got the 1. Same thing here. If I do the NOT on a 1, I get the 0. And here you can just see the mathematics of it. It's very simple. If you multiply this matrix by this vector, you will get the opposite vector. So what I showed you now is that I took this qubit, and by the way, this qubit was real. It could also be complex. And all I did was just do an operation on it. And the operation I did was a NOT operation. Let's see another kind of operation. It's called the Pauli Z gate. This one is a little bit more interesting. When it acts on a 0, it does nothing. It's like a unit matrix. By the way, you see that this is very similar to the unit matrix, only we have the minus here. So when you multiply the Pauli Z gate, when you operate on a 0 bit, it remains unchanged. When you multiply it on a 1 bit, it becomes a minus. Okay? That's another example of an operation. The most popular operation that we will work with in the coming 2-3 lectures is called the Hadamard gate. This is how the matrix for the Hadamard gate looks, and this matrix already does something really, really interesting. So when I operate the Hadamard on the 0, and please, you can see it here, this is the Hadamard, and this is the 0 vector. When we multiply it, we get this vector, 1, 1. But what is 1, 1? 1, 1 is really 0 plus 1. Okay? So what we are seeing here is that when you take, this is really, really interesting. When you take a Hadamard operation, when you take a qubit and you Hadamard it, it immediately becomes a superposition of a 0 and a 1. So you took like a pure qubit. This is the qubit. You bombed it with a Hadamard, and suddenly it becomes, you split it in a way. It becomes a superposition of 2. And when you do the same to the 1 bit, again, just simple matrix multiplication, becomes another kind of a superposition. It has a minus here, which in most cases doesn't mean anything, but in many cases it will. Okay? But you can see that we took a qubit and we operated on it with a matrix. And what happened to this qubit specifically, it became from a healthy, simple, boring bit, it suddenly became a superposition of 2 bits. And if you remember, I will happily show you next time that I could also take another matrix which can create this kind of a superposition. Okay? There's another gate which will do a superposition which is not symmetrical. There are many, many, many gates at our disposal. Again, not going into mathematics, we'll do it in the next lecture. These matrices are called unitary matrices. In the real world, they're similar to orthogonal matrices or to rotation matrices. So unitary matrices are the rotation matrices of the complex world. And it's important for us to have some kind of a rotating situation because we don't want the qubit to become a shoe after you multiply it. We want it to stay a qubit. In other words, we want it to be at the same length. We want it to have a length of 1 if it started as 1. So all the operations must be, we have to have a limited kind of operations, and they're all rotation-like operations, but in the complex world, and they're called unitary. So all the matrices that you will see, and there are hundreds of them, they're all maybe Yeah, hundreds of them. They're all unitary matrices. Okay, otherwise they will change the nature of a qubit. And all we want to do in a qubit, in a way, is to rotate it in the complex world. But we want it to stay a qubit. Okay. We're moving in a very nice rhythm. I'm happy today. So what I'm showing you now is an example of a quantum circuit. It's a relatively old version of the IBM composer, which we will all together work on now. But I want to show you philosophically the concept of a quantum circuit. So what you see on the left is, first of all, we have 5 qubits. That's all. They all started in the 0 state. Now, as you can see, we're starting to multiply them by matrices. So Y is an example of a gate. This is the Hadamard that we saw a minute ago. You see the H here? Sorry. This is the H that we just saw, and we'll also see the X in a minute. So this is the X, you see, that's a knot. So for example, this qubit, after it was operated by the X, it became 1, right? Because it flipped it. Then it was Hadamard. And here is something really interesting happened. You see that this operation is an operation between 2 different qubits. Most of the operations just work on 1 qubit, like this one, like this one, like this one, but some of them actually connect 2 qubits. It's called a CNOT. And believe it or not, this is how we're going in the next lesson create entanglement. So we're going to take, just think about, we're going to take 2 qubits on a IBM computer, which is somewhere in Georgia or North Carolina, and we're going to actually make them entangled. It's just crazy. Using the miracle of the cloud, we will take 2 physical elements and we will make them entangled. And it's really amazing. I mean, I think, by the way, that next lesson is probably going to be the most thought-provocative lesson that you've had, because you're going to see with your eyes the level of weirdness that quantum mechanics can go. Okay, so that's a classic circuit, a simple one indeed, but we see we have 5 qubits here, and we start to bombard them with operations, with matrices. Okay, we just start to bombard them with Hadamards, with X's, with knots. And after we finished, here we finished the bombarding. So after this stage, each qubit here, Q1 here, is very different after all these tortures that it went through. So look, we didn't only flip it and caused it to be in superposition. We even had it entangled with other qubits. It's really a torture room to these qubits. But after we finished this stage here, all of the qubits are still in the same place. They are just very, very different than what they were in the beginning, because we bombarded the hell out of them with unitary operations. Now comes the dramatic moment. We're starting to measure them. So we measured this one, and it became a 1. And we measured the second one, it's a 1. I mean, these all have to be 1 or 0. It's a mistake here, of course. It's just the number. But each measurement here will just give it a 0 or 1. So each one of these 5 will just be a very boring 0 or 1 after the measurement. But that's basically the flow of things in a quantum computer. You start with input. You do a lot of things to the input. Then you do the measurement, and you get boring regular bits. I think it reminds us a little bit of machine learning. Remember that we started with an input layer, then we had many layers that interacted with the elements from the input, and then we had some kind of an output layer. I hope we'll have time to see how these 2 amazing fundamental pieces of science can really interact together and work together to the best of humanity. But before we go, I promised you that we're going to create a real circuit together. So let's do it. But before that, just a quick summary. So we learned that qubits are 2-state physical systems. They can be atoms, they can be photons, they can be whatever you want, okay? It all depends on what kind of a computer you have, of a quantum computer you have. They can be operated on by a wealth of unitary operators. So these 2/2 matrices or 4/4 matrices for entanglement, they just multiply these qubits and change them, obviously, rotate them in complex plane. Qubits can be pure states, mixed states, or entangled states. We show that according to the operations you apply to a qubit, it changes. And most importantly, once measured, they lose their quantumness, they lose the magic, and become regular, classical, boring bits. Okay? So let's end the lesson by just a simple example of a real quantum circuit. So what you're seeing now is called the IBM Quantum Composer. I urge you to go to Google, just write IBM Quantum Composer. You'll get a very similar page. They may ask you to sign in with your Google account. You don't even have to pay money. And what you can see here is a platform to build a circuit. The beautiful thing is that we will be able to run the circuit on a real physical quantum computer by IBM via the cloud. But first, let's start with a very, very simple circuit together. So we have only two qubits, this one and this one. You can see, by the way, on the right here, that their value is 0. So we have two 0 bits. If I want to change this one to a 1, what do you suggest I should do?
The not.
Let's do that. Let's look for a not. Hey, this is not, right? All I'm doing is dragging it here. Now look at the right. Oh, what happened? Beautiful. So you see now that I have a 1 here. What happened if I take another not? Before I leave, what happened? It will go back to 0, right? Now what you see here on the bottom, 0, 0, it means that both qubits are 0 now. Okay? If I now kill this one, then now I have one qubit is 0 and the other one is 1. Okay, let's do something crazy now. Let's take a Hadamard gate. I have to find it first. Oh, it's the first one. It's the most popularly used one. So let's put it here. And now things will become interesting. Let's try to analyze what we have here. So this one was originally 0, but we changed it into a 1 by putting the not here, right? So what we have here is a very boring one bit. So Q0 is just a 1. Do you agree? But Q1 is Hadamard. But let's see what Hadamard does to a 0. Okay? When Hadamard operates on a 0, it creates a superposition of a 0 and 1. So this one now is a combination of 0 and 1. So this one is 0 and 1, and this one is 1. So my situation here is very interesting. If I want to look at the complete picture, I have 1, the last one is 1 anyway, so the Q0 is 1, but then here I have 2. I have a 0 and a 1. So I have a 0, 1, and a 1, 1, because the 0 here connected with the 1 here gave me this 0, 1, and the 1 here connected with the 1 here gave me this 1, 1. Okay, let's do something really crazy, and I'm sure no one will be able to guess it, but let's try. What happens, do you think, if I take... by the way, you can see here on the right, as expected, because this Hadamard split it into a combination of a 0 and 1, I have here half-half. So I'm not surprised. Now let's do something really crazy and take a Hadamard and put it here. So, as expected, I have half-half here and half-half here. But could you say why would there be a little difference between these two? Again, I'm looking at the qubit after this Hadamard and after this Hadamard, and I see that there's something a little bit different here.
Because of the minus?
Beautiful. So let's see, when we multiply the Hadamard on the 0, it gave us a 0 plus 1. When we multiplied a 1 with the Hadamard, it was a 0 minus 1. If we go back, this became a 1. Remember, this is not a 0. So here we Hadamard a 1. And the minute we Hadamard the 1, we caused a minus. And just to show you that I'm right, what happens if I kill this here? Everything is positive. So now what I have here is a 1 plus 0 here, and here also a 1 plus 0. So the combination of the 4 is 0, 0, 0, 1, 1, 0, and 1, 1. So this is a way to look at the way the system is now. So this is the simple circuit. Again, does anybody know what happens if I put a Hadamard here? Well, you can see the result. When you do a double Hadamard, it's like the unit matrix. Okay?